All right, so this is our Physics 212 project number 2. And this problem, so the problem is that we chose to do is the buoyant force problem. And in this problem, it is asking and states, an object that is immersed in a fluid such as water or air will experience a force due to pressure or displaced fluid, which is known as the buoyant force. It wants us to construct a model for this force, use this example to explain real world phenomena such as why some objects float, sink, or such as a hot air balloon, which will rise, float, or fall through the air. So here are some of the goals that we want to tackle throughout this project. So we want to see what pre-existing knowledge do we know that will help us. We would create free body diagrams. What are the equations that we're going to be using and how we found them? Which assumptions were made during these for these equations that we used? And situations that we can apply our math to, and as well as why this makes sense and how to apply these concepts to other problems. So some background information. So the buoyant force, what exactly is that? It is defined as an upward force that is acting on an object partially submerged in liquid or air. And another thing that you always hear when it comes to buoyancy is Archimedes' principle. And this states that an object submerged in fluid is subject to an upward buoyancy force that is equal to the weight of the fluid that is displaced by that object. Another thing that also will affect buoyancy is density. So different liquids and different gases have different density. So for example, in a hot air balloon, the hot air allows the hot balloon to rise above the cooler air. And said the opposite. If you have cooler air, it's going to descend from the hot air. So in part 1, we're going to understand the plan and what we're going to be doing today. So some assumptions that we're going to make in this is that gravity is going to be constant throughout the entire object and liquid that we're going to be looking at. And we also know that liquid is going to be in equilibrium. And what we mean by this is that the liquid is not going to be moving. It's going to be static and stationary. And we also can assume that the density of the liquid is going to remain constant. And so what we mean by this is that the liquid is not going to compress or get any denser. And the same assumption can be made with the air. The air would not compress. We also can assume that the liquid has no friction on it. So we can assume that it's not going to stick to any of the objects that we're putting into the water. And then our final assumption that we're going to be making is that the mass of the object is evenly distributed. So it's not going to be different throughout. It's going to be evenly distributed. So here's some physical representations of what we are going to be talking about in a free body diagram. So in these, we have a diagram of an object submerged in water. So in the equation, you can see that the buoyancy force is equal to the force 2, which is the gravity pulling down, minus the force 1, which is going to be the buoyancy force. And that's going to equal to each other. And we can see that in the free body diagram of the object itself. The buoyancy force is pushing up and the mass and the gravity is pulling it down.
Hi everyone, my name is Ella Jones and I will be presenting the calculations part. So we all know the buoyancy is, as introduced in the previous slides, the force pushing up an object anytime it's in the water or in any type of fluid. So in order to solve this, there are some variables that we have to know. Those variables being V for volume, rho for fluid density, H for height, capital P for pressure, L for length, F for force, G equals gravity, A is area, M is mass, D is density, and W is width. And all of these come into play at some part, which is why I am bringing them to light now. So, as described previously, I just said this buoyant force is an upward force on any object submersed in fluid. So a quick Google search can give us the formula for buoyant force, which is defined as the buoyant force equals the fluid density times gravity times volume. We must find a way to get this formula using concepts we already know. So here's some equations that we need to know. Hydrostatic pressure is a big one. So that pressure is going to equal rho times gravity times height. And the height is the height of the object in the water. The pressure is force over area. And then if you rearrange that, you can get force equals pressure times area. And then a really important one for the future is volume equals mass over density. So finding this symbolically, so first we have to take the hydrostatic pressure formula, which I described before, and you can plug in the the hydrostatic pressure formula the into the pressure in the force formula, into the force formula, which will get you rho times gravity times height times area. Since area is length times width, and volume is height times area, that means that you can consolidate that into rho times gravity times volume. And if you wanted to go further, depending on the variables that we are given in the model or in the problem, volume equals mass over density, which final answer could be for the force of buoyancy is rho times gravity times the volume of the object. And keep in mind that rho is going to be the fluid density. So it's the density of whatever fluid that your object is submerged in. Or it could equal rho times gravity times mass over density. And density is in density of the object. So I'm going to start making sense of the work. So here are my unit sense making. So the unit for a buoyant force is newtons, which is the same as it is for every other type of force. Another way that we could say newtons is kilogram meters per second squared. This isn't important now, but just wait until we get into the calculations. If you read on the other side of the screen, you'll see. The units for each variable in the equation are listed there. Um, when the units are plugged into the equation, it might be confusing, as you will see that the unit that I got ended up being kilogram meters per second squared. But as I previously discussed, kilogram meter per second squared is also equals to Newton. So whenever you plug everything in, kilogram meters cubed times meters over second squared times meters cubed, you will get that the force of buoyancy equals newtons, which is what we were hoping for. Alrighty, thank you.
Hi, I'm Jen. And now that we explained and we know what buoyancy forces are, let's do some sense making and try to do it in context. So, in this context, we're going to use what we know about buoyant forces to see how things float or sink. So, in this situation, I have two boats. Um, Ella, my group mate, is in the first one, and Kanoa is in the second one. So Ella's boat has a density of 640 kilograms per meter cubed, and she is sitting on water with a density of 1,000 kilograms per meter cubed. Kanoa's boat is much more, has much a bigger density, and he has 2,000 kilograms per meter cubed, and he is also sitting in a different fluid density of water with 1,200 kilograms per meter cubed. So now that we know our two situations, Ella gave us the buoyant force formula, which is buoyant force equals the density times gravity times volume. So our first boat, I calculated the buoyant force for the boat using what we know. So gravity, we use 9.8, and then um, we have the given volume. And so we got a buoyant force for the boat of 2.2 newtons. And then we also calculated it for the water alone. And so we have 2.2 newtons for the boat's force, and then 3.7 newtons for the water's buoyant force. And as we can see, the boat's buoyant force is smaller than the water's buoyant force, sorry. Kainoa's boat, putting all the values into the formula, we got 0.5 newtons for the boat and 0.3 newtons for the water. And it's different, and Kainoa's situation is different because the boat's buoyant force is actually bigger than the water's buoyant force. So what does that mean? It means that Ella's boat will float and Kainoa's will sink. Because the boat's buoyant force is smaller than the water's buoyant force, it will float. And if the boat's buoyant force is larger than the water, then it will sink. This can also be explained in another context in a hot air balloon. It's the same thing with the same formula. So we have the helium density and the air density, and then we have the downward gravity force, and of course the volume. So the buoyant force can also be applied to a hot air balloon of whether it will float or fall. And for reflection, um, okay, yeah. For reflection, what we learned about buoyancy force is related to simple harmonic motion. We talked about that um, weeks before, and the principle behind simple harmonic motion is that a pendulum will be moved from side to side, and it will go to equilibrium by a force called restorative force. Sorry, and this relates to the topic of buoyancy because, as we talked about in the beginning of the presentation, buoyancy pushes an object back up to the surface or down to the surface, and while these forces are not the same by just term speaking, it works the same way because um both topics they all have the same motion attraction. So simple harmonic motion is going side to side, and buoyant force can be looked at as going up and down. So specific simple harmonic motion problem that we discussed earlier, I think this was week 5's homework. This question is asking the amount of time it takes for the pendulum attached to a tree to return to equilibrium after being pulled at a certain angle. And this is similar to a problem maybe asking in buoyancy how long it would take for an object in water to reach a surface. And both will all be considered equilibrium when they want to reach a surface or if they want to go back to the original position. So yeah, there is more real life examples. A submarine, um, it changes its weight to go up or down in the water. When the weight is greater than the buoyant force, it will sink, of course, because the gravity force would be the gravity and mass force is going to be greater, so it'll go down. And if it is lighter, then the force of the water density will push it up. And so yeah, we talked about the hot air balloon. And it works both in a liquid and gas form. When a hot air balloon adds hot air, it will rise, and colder air is more dense, so then it will go down. And that is all for the video project, and this is our works cited. Thank you so much for listening.